Hello, this is Charles Anderson again, and I'm trying to explain the use of Aspen Custom Modeler. Today I'm going to try and have a look at how models are put together, and in particular look at the slightly confusing topics of component lists and structures, as well as the basics of putting together your first flow sheet. Okay, so let's start with a blank Aspen Custom Modeler. The first thing you need to do when you're putting together a set of models is to define the ports, the connection point between streams and unit operations. So to do that, you come into Custom Modeling Ports, add a new port, and we're going to call this one Mass Only. And so then what we're going to do is we're going to define the connections within that port, or the variables that can be used within that port. I'm cheating and I've written the code somewhere else already, so I'm just going to copy it across to save you watching my terrible typing. But what I'm going to do for this mass only port is I'm going to define a variable f, which is going to be mass flow rate, and a component z, which is going to be an array defined by component list of mass fractions. I give both variables a description, and then just to help with initialization, what I'm going to do is by default, I'm going to say the value of z that it's going to take by default is 1 over the size of the component list. So if there's 2 components, they'll both be at 50%, 3 at 33%, and so on. So that defines my port. I'll compile that. It compiles without any errors, so that's a good starting point. So I've got a port, so now I can connect things together. The first thing to do then is to create a stream, and I'm going to create a stream that I'm going to call a mass stream. And you can see it's giving me some hints as to how to set up this mass stream. What I'm going to do initially is, again, just copy over the variables from another model. I'm going to have a pair of ports, so I'm going to declare an inlet port and an outlet port. So this is saying I'm going to use this port type mass only that I've created. I'm going to create a port called in main, and it's going to be an input. And then I'm going to have an out main, which is going to be an output port. So this one brings stuff into the stream. This one sends stuff out again, discharges from the stream. What I'm then going to do is I have to create variables, or sorry, equations to describe what's happening with those ports. So what I'm going to do is I'm going to say, I'm going to give the variable, sorry, the equation a name. I'm going to say set f, so set the flow rate, and I'm going to say the outlet mass only, and if you remember, the mass port has variable type f in it. So the f variable in the outlet port is equal to the f variable in the inlet port. And here I'm setting a whole array. So z is defined as a whole array. ACM is smart enough to recognize that z is an array and that the sizing of that array is the same on both sides. So this is actually n equations where n is the number of variables, and for each one it's saying z out is equal to z in. Okay, so let's compile that, make sure it works. It does, so that's good. I've got my basic stream put together. If what I do is I take this stream and I put it onto the flow sheet, you'll see I get a couple of warnings. First off, default is not initialized, and I'm underspecified by 1. So first off, let's come in and work on default. What I'm going to do is, rather than using the Aspen physical properties, I'm just going to use a very simple list of equations. So I'll convert that into a set. That then lets me come in and have my variable names. I'm going to create variable A, B, C, and D. So these are my components, the very creatively named A, B, C, D. Okay, so now I've got 4 equations. The validation has said it's okay, so the validating is complete. But if I look now, I'm 5 degrees of freedom underspecified. And if I have a look what those degrees of freedom might be, it's saying, well, you haven't told me what the flow or composition is, you silly person. Okay, so that I can do either by coming into the stream and fixing those variables. So I'd say I fix the inlet. But what I want to show you is a slightly smarter way of doing that. I can use the structure of ACM to determine what the what's going on. So what I'm going to do is I'm going to say I'm going to copy these variables over. So what I'm going to do first off is I'm going to create an array of variables for an unbounded Z. So my mass fraction in an unbounded basis is an array that's based on the component list. Then what I'm going to do is I'm going to come in and I'm going to say if my inlet stream is connected, so if my in main is connected, in this case it's not connected, but if it were connected, then I'll just say this new array that I created, ZUL, is equal to the incoming component mass fraction. Otherwise, what I'm going to do is I'm going to say it's equal to the normalized value of those ZULs. So you can see I'm saying for each component in component list. So in this case, I could write it as an array, but I've chosen to write it explicitly, and I'll show you why in a moment. So I'm saying whatever value ZUL takes, I will take the sum of those and then divide the individual component by the sum to give me my mass fraction. This lets me put in ZUL as, pounds or kilograms an hour, or the dry weight basis, and have it renormalized for water. All sorts of clever things like that are possible by taking this small trick. The other thing I've done, you'll notice, is as well as naming the equations, I'm naming the if block, so that when the error messages come up later, it gives me some clues as to where those errors are coming from. Not that there's ever errors in my models, of course. Okay, the final thing to do then is to make the problem square, which was where I was starting in the first place. So what I'm going to do is I'm going to say if the inlet is not connected, then fix this array of ZUL and also fix the flow rate. So that's giving me n+1 degrees of freedom, which will hopefully address my 5 degrees of freedom that I'm under. So let's compile that. I've got no errors, and you see my model has now become square because I've got the right number of things that are fixed and free. And if I come and have a look at the all variables table, you can see my ZUL is is defined. My flow rate is 1,000, but interestingly, it's going to be difficult to initialize ZUL because it's all set at 0. So I'm going to pull the same trick as I had in the port. And so rather than retype it, I'm just going to steal it from the port, where I'm going to initialize ZUL to be actually, you know what? I'm not going to, yeah, I'm going to do that. So rather than initializing them all at 0, I'm going to initialize them all at 1 for now. So that way, so I'm going to demonstrate, the advantage of doing it this way is now, okay, they're all set at 1, but because I'm renormalizing, it'll renormalize that to 0.25. So let's just confirm that. Let's hit run, and you can see, not very interestingly, it's all at its default values, so it's run. But if I make, make the flow 200 and I have twice as much B as I do everything else, you see it does now renormalize successfully. So that's all looking pretty good. Okay, so I've got my stream and I've got my port, and I've done some cool stuff in the stream and port. Just for the fun of it, because I always find documentation helps a little bit, I'm going to put some structure into the way I've got the model set up. So I'm going to say these are my initial conditions, or my local configuration, and here are my equations, so I can change exactly what's going on there. Yeah, you can put in other comments around the place. I'm just doing this for to help me see the structure later on. Okay, so I've got my stream, I've got my port, I've configured it as a feed. So now let's create a small tank or a holdup so we can see what's going on there. Okay, so I'll come into models, I'll create a new model that I'm going to call holdup. And again, I'm going to cheat and copy some equations over from another model that I had. Here's one that I prepared earlier. So for this, I'm going to define some new variables. So I'm going to come in and I'm going to have my inlet and outlet port, same as I had for the stream. I'm now also going to have local variables for the total mass held up in the tank, the mass of the individual components held up in the tank, and the rate at which I'm creating material, my rate of reaction, if you like. That will then let me come in and do some equations. I'm just going to skim through this because this isn't really about how to do mass balancing. But so what I've done now is I've created my equations, and what I've done is I've said the $ means d by dt. So what I'm saying is for each component I in the component list, create a variable called compval, where I'm saying the d by dt of mass, so d mass by dt of that individual component is equal to the flow in times the mass fraction in minus the flow out times the mass fraction out plus the rate of reaction, which by default is fixed at 0. I'm then saying my total mass is the sum of those masses, and my mass fraction out, my Z out, is equal to mass of component I divided by the total mass. So that should be a complete model. I can run that, and it converges, and it's happy. What I can do then is I can just test it by dropping it onto the flow sheet, connecting up my stream to the inlet port, and you'll see what happens is I'm 1 degree of freedom underspecified, and that's because I've specified the flow in, and in a normal mass balance, the flow in equals flow out in steady state, but I haven't actually told it that. So what I'm going to do is I'm going to come in, and for now I'm going to fix my mass at 10 kilograms. You see the problem is now square. I can run it, and you can see the outlet fraction is equal to the inlet fraction, the outlet mass flow is equal to the inlet mass flow, and the model is behaving pretty much as I would expect it to do. Okay, so that's looking good. I've got my my model set up, I've got my hold-up set up, I've got some differential equations, I've got an array, and I've shown how the degree of freedom in steady state. I needed to set the mass. If I switch over to dynamic mode and try and run the model, what it'll tell me is that it's structurally singular. That's because I fixed the mass. I can't do that in dynamic mode. I have to free that and then, for example, fix the outlet flow rate. So right now the flow rate in and the flow rate out are equal, so the mass will stay the same. Let's just demonstrate that by running for a little bit. But if I now slow down the rate at which stuff comes out, you should see the tank starts to fill up. And so there you go. Basic chemical engineering, not very exciting, but good enough to demonstrate what's going on. Similarly, though, if I come back into steady state mode, it does say it has a solution, but it's going to be really, really difficult to find it. So I'm going to free that and fix the mass again just for steady state. Okay, so that's all well and good. One thing that's kind of interesting, though, is if I look at these equations, I have a slight potential problem in that although this mathematically will sum to 1, this array, each of these equations is actually only solved to the tolerance of the system. And there is a danger that the z's, the mass fractions leaving, will not sum to 1 if stuff starts moving around fairly rapidly. And it's interesting that if they don't sum to 1 and I pass that array into the Aspen physical properties data calls, it tends to cause bad things to happen. So there's a trick I was going to show you to help make things sum to 1. What I'm going to do is I'm going to create a new component list called key. And I'm then going to use that component list to replace some of these equations. What I'm going to do is, rather than saying I'm summing over the whole array, I'm going to sum over the array less the components in key. And if I choose only one component for key, that'll give me n-1 equations. And then for the nth equation, what I'll do is I'll say, and I'll force the sum of z's to equal 1. What that's going to do is it's going to guarantee that my sum of z's is going to equal 1, but I've got to create this new component list called key. How am I going to do that? Just check to make sure it works. It does, it's happy, but now I'm under by 3 because I haven't defined that key component list. So I'm going to come in, I'm going to create this new component list called key, which I'm going to set that way. And for the purposes of this model, I'm going to say that D is my key component. And so now what's gone wrong is that I haven't successfully, on the stream, that's why. What's happened is I've got this variable key, but it's currently pointing at the default component list. So right now, what it's saying is component list minus the same component list. So it's ignoring all these equations. What I want to do is change that key from default to key. You see now I've gone square. Now this key contains just that one element D, whereas default contains A, B, C, D. So this is n minus 1. This is the nth equation. I'm all square. The world's in a good place. So what I'm going to do is I'm going to come up here and I'm going to make that equal to, actually no, I'm just going to leave it for now because there's something else I want to show you in just a moment. Okay, so I've set up my key component. I've defined it here. That's all good. I'm going to pull the same trick in the tank. Again, in the tank, my hold up model, I want to create that array key. And you can see here I'm actually initializing it as key, so I'm going to do the same thing over on the stream just for the fun of it. Compile. And then in the tank, what I'm going to do is I'm going to change out the calculation for the mass fractions out to use that array key as well. So now you can see for n-1 equations, I'm saying mass fraction out is mass of component over total mass, but I'm summing them all to 1 just as a trick to try and keep my sum of z equal to 1, and that's going to save me trouble later on. Okay, so that's all looking hopeful. That's all square and converged. If I come into here, you'll see that I've created the variable key, but it's at the default value key. And in fact, what I can do is I can come back here and reset this to default. So that's key as well. So that's all looking pretty good. Okay, the final thing I want to do though is it's possible that in different parts of the flow sheet I want to use different component lists. So one of the powerful things that I can do is I can create a structure. A structure is kind of like a global variable, but it's more of a holder for variables and possibly equations, so that you can make sure that they're the same across multiple instances of stuff in a flow sheet. So let me come in and create a structure. What I'm going to do is I'm going to call it main props. Sorry, I'm just setting up my cheat in the background. Main props. And so what I'm going to do for now is all I'm going to do with that structure is create the value key. So it's the same definition as I used in the other parts of the system. So I'm going to compile that. So now I've got a structure, and now what I can do is if I come into the stream, rather than relying on the other system, I'm going to instantiate, I'm going to call props an instance of this new structure key props that I've created, and by default I'm going to call that structure props. It's all getting, the names are all collapsing on top of each other. I'm sorry for that, but hopefully it remains clear. Okay, so if I do that, now what I'm going to do is I'm actually going to, in my local configuration, I'm going to make, I'm going to define the default value of this key as equal to my props.key. And then, so let's do that. Let's compile that. And what you see is I've got a problem And the problem is that I haven't yet created an instance. So if I come to my flow sheet, I don't have any structures. So I'm going to create an instance of my generic structures type. And I'm going to call that props, if I can type, props, which is matching the name props here. So I've created an instance of it. Now you see there's a folder of structures that's been created, and this type props has been created. And if I go into there, you can see that has got basically two variables inside of it. It's got the component list, which at the moment is set to default, and the key component list, which is currently set to key. If I come up to my component lists, you see I've got one called default and one called key. So that's all looking good. That's initialized correctly. I've got my props there. I've got stuff happening over here, and now my stream is using the same key as the props. So what that means is I'm forcing all the instances of my stream to use that same props system, if that makes sense. So let's pull the same trick on the holdup. So again, I'm going to come in, I'm going to declare props as an external instance of the props component list, and I'm going to give myself this local configuration that lets me define key. Now the other fun thing I can do over in the stream is I'm going to go back to setting ZUL to 0 by default, but I'm going to make Z_UL, it's not case sensitive, but I am geeky like that, key 1. So now, compile. So now if I come into the stream and I set all the systems to default, you see, because I've defined D as the key component, and for example, it might be water, now by default, the stream will start off as all water. So there we are, we've reconverged the model and it's all water. So that's good. The final thing I want to do then is make sure I've compiled that hold up correctly. Yep, I'm all square, that's still looking good. So I've got the hold up set up, I've got the key component set up, and I've got the structure set up. Just for fun to demonstrate why this is useful, I'll create another stream and another connection. And again, I need to fix the mass to keep the problem square in steady state. So the problem's all set up. So that's good. But now what I'm going to do is I'm going to come in and I'm going to create two new component lists. I'm going to call it area 2. And in area 2, I'm going to have components D, E, and F. And I'm going to create a new area 2 key variable, which I'm going to make a set. And so now I've got my area 2 key, and that's going to be F. Actually, you know what? Just to be consistent, let's call it D, if we're pretending D is my watery component. Okay, so now if I look at stream 2, it's using key and default, and it's using the structures props. I'm going to create another instance of my key props. So I'll create an instance, and I'm going to call this area 2 props. So I then come up to my flow sheet structures. I've got that area 2 props that I just created. If I look at the variables for area 2, that's using default and key, but I'm going to change that to use the area 2 component list and the area 2 key. And so now if I come to the stream S2 and I change it from using the props component, the props structure, to using the area 2 structure, nothing happens because I failed to remember to do something. The joys of doing demonstrations. So what I'm going to do here is I set keys, and I think what I need to do as well is to say component list is props dot component list. So now you see it's changed the array, so it's DEF instead of ABCD. It's looking at area 2 for its component list and area 2 key for its key component list. Interestingly, I've gone underspecified by 3, and why is that? That's because the tank is not, so I've got DEF coming out of stream 2, and I've got ABCD coming into tank B. So let's just make sure I've set up the tank 2. So I need to make sure tank 2 is component list is equal to props dot component list. And so now if I open up tank 2 and I change its structure to be using that area 2, you'll see now it's moved it all to DEF, same as the other one. My problem's all square and I can solve it. So it's not a great example, but this is why structures are really useful. It gives you a way of changing one single variable or one single element of a model and changing a large section of or a swathe of ways that the equation is working. Okay, I think I'm going to stop there for now. That's structures, component lists, why component lists might be different in different parts of your flow sheet, and the very, very starting basics of putting together a flow sheet. I'll try and do another model or another recording shortly. In the meantime, it'd be great to get any feedback. Like it, give me a comment, ask me some questions. I'd be happy to try and help. Okay, thanks. Goodbye.